Okay, so let us start. So let me start off from where we stopped yesterday. So remember, we looked at the case when I have some surface, let's call it S, living in a larger manifold. Let's call it M. So on this manifold, I have the metric G. On this manifold, I have, let's say the metric, let's call it H for the moment. We'll change it later. But it's a sphere, so let's call it again Q. Then on this, let's call it ambient space M, we have the connection, let's call it nabla. And on this space, we have the connection, let's call it D. So this combination of this, the manifold, the metric, the intrinsic derivative operator, and here the same things. And here we are assuming now that this Q is non-degenerate. And we are working now in the case when this surface S has codimension 2. So you have to imagine now a sphere embedded in your four-dimensional manifold. And the sphere is then this surface here. So normally you should think of the whole sphere. And it has two normals, right? As we discussed last time, the codimension is 2. And the tangent space orthogonal at any point to this manifold is a Minkowski manifold. So it has a time-like and a space-like direction. So that means it has two null vectors, L and M. And then as we discussed, we have if I take any two vectors X and Y tangential to S, then I can always decompose grad XY equals XY. So that is the tangential part of this vector. And then I said, I use the second fundamental form acting on X. So now there's a little sign convention issue that one of the students pointed out to me yesterday. So in fact, what we will do for the moment is a little change of notation to get sort of to agree with the literature as the physics literature. I will just call this K, XY, okay? So this K is a vector. So for every X and Y that you plug into K, I get a vector. So this K is a vector of this form. So it's two indices covariant and one index contravariant. Okay? And it's a linear function X and Y. That's why it's a tensor of this kind. So this combination is essentially this K CAB times XA YB. The result is a vector. Okay? So this should be now, this is just a brief summary of what we did yesterday. Is that clear? Any questions about that? Okay. And then we also then saw that this KAB C is of the form of negative. Let's call this B and C minus so this is sort of intuitively it makes sense because this is the extrinsic curvature of that surface S in the connected with the L normal, and this is the extrinsic curvature of the surface S connected to the N, and this comes with the N, and this comes with an L. And these two indices are tangential. So often you might see in the literature these have a uppercase A and B to indicate that these are sort of indices living on S, while this index is orthogonal to S. Okay. So if you wish, I mean, if this confuses you, then you can call this as K, big A, big B, perhaps here mu, just to indicate that this big A and big indices are meant to be indices on the sphere, so angular coordinates of some kind. And this index is the one normal. And the normal space is two-dimensional, so that's why I have these two different terms here. Good. So now the mean curvature vector, let's call that H, C, is then the trace of this K using the induced metric on these two indices. Okay. So this is simply Q, A, B, K, C. So this is the mean curvature vector. And once you write it in this form, then it's clear that this is of the form of minus theta of L times n minus theta of n times L, where these thetas are the null expansions. So theta of L is the expansion of the vector L, and theta n the expansion of the vector. Right? So then theta L. We just, sorry for the confusion, let's call it Q tilde. We will use, you'll see why. Tomorrow we'll use always this 2 meter with a tilde. So this is Q tilde AB. And theta of n. Okay, so these are the null expansions, and this is what you calculated yesterday. Using, in my view, not a good method with the 4 divergence, but fine, then you got to be careful with other things. You should try to calculate this explicitly in this form with the Christoffel symbols. And tomorrow we'll see a better way to do that with the Newman-Penrose formalism, but these are the definitions of the 2 expansions. Okay. So let's understand the meaning of this expansion, right? So let us try to think what this expansion would be for, let's say, a normal sphere in this room. Okay, so just imagine now exactly a round sphere. And what do the expansions mean? Well, if I imagine now shooting beams of light, let's say in the outgoing direction, then you see that the beams of light, since the surface is sort of bending convex in that direction, these light rays will diverge from each other, right? So that means that for a normal sphere, the outgoing light rays will be expanding. So that means that if I call that null direction to be L, then for this normal sphere, then theta of L is positive. And if n is the ingoing vector, so that is a vector pointing inward from the sphere, so they'll be all converging inside. So that means that theta L is positive and theta n is less than 0. Thinking in terms of mean curvature vector, so if you now imagine theta L is positive, so this is a negative number here. While if this is negative, theta n, that's a positive number here. Okay? So if you now imagine a diagram like this, so this is, let's say, L. This is n. These are the opposite directions along the negative. So what is the causal? Is it a time-like, space-like? What vector would this be for with these conditions? Okay, so imagine now this is positive. This is positive. It's negative n. So this is negative n. This is negative L. So I take then negative n, add to it a positive L because that is negative. So then in this, for a normal sphere, I get vector like this. So a space-like vector. So this is what you expect normal for normal spheres in flat space. And even like we did the calculation yesterday, if you do the expansions for, let's say, the usual 2 spheres in the Schwarzschild case, if we're in the exterior region, again, this is true. So it is true that this is positive and this is negative. But you found that, in fact, at the horizon, so this is the exterior Schwarzschild. But at the horizon, you found that theta L was 0 and theta N was still negative, right? So this is, let's call it the horizon. In this case, theta L is 0. So this vanishes. So the mean, and theta N is negative. So the mean curvature is along the L direction with a positive sign, right? So in that case, it goes along here. So this is the exterior. This is the horizon. And finally, if you were to do the interior of a Schwarzschild, then what you would find in fact that, well, for the interior, you find that theta L is in fact negative and theta N is in fact negative.
Hi.
Yes.
I think the analysis that you did yesterday and this hold it for space-like surfaces, right? I mean, you have to refine the arguments a bit for null surfaces like the horizon.
No. This is still space-like. We're looking at the two spheres, remember. So we are looking at the codimension two surfaces.
The horizon is a null surface, right?
No. We are looking at R equal to constant and B equal to constant. So it's a sphere. So even in Schwarzschild, as you rightly said, we have the. So we'll do the null surface thing in detail tomorrow, not for today. At the moment, we are just looking at cross sections of the horizon. We're not looking at the entire horizon. I'm just taking now two spheres of fixed radius and fixed time. So that would be a two sphere. This would be, in the Penrose diagram would be just the dot here. We're not looking at the entire null surface. Okay. So it's always, as I said here, we're looking at two spheres and we have a codimension two surface. I have not yet told you how to do the analysis for the full three-dimensional surface, which we will do in detail, I promise you. But at the moment, everything I said completely holds, is completely valid for any part of any sphere in Schwarzschild. Okay. So once I go to the interior, then both of the expansions are negative. So in that case, you see that it's both of these terms are positive. So then in that case, I get vector here, right? So this is then in the interior. So then inside the horizon, the mean curvature is time-like, outside it's space-like, and at the black hole horizon, it is null. So a surface here is said to be a trapped surface. So this is the trapped surface. So let's call it trapped. This is untrapped. And this is the marginally trapped surface. So marginally means one of the expansions is vanishing. Okay. So this is, let's call it marginally trapped. So now this notion was introduced by Roger Penrose in the context of his singularity theorems. So far in the previous lecture from Thomas, you heard about the event horizon and the existence of that to show that they define what a black hole is, right? So now keep in mind, there's a different way to define what a black hole is. Well, a black hole is a space-time which becomes some singular sometime at some point or the other in the future. Okay? So I won't discuss that point here in detail, but the fact is that if a space-time has a trapped surface, if you can find a trapped surface in a space-time at any given point, then at some point in the future, there will be a singularity. So this is then the famous singularity theorem. So then this tells you that, well, the existence of such a surface is the signature for there being a singularity for sure. And if you believe cosmic censorship, then there should be a black hole horizon of some kind in that space-time. So, and then one might think naively that, well, this marginally trapped surface case should be the boundary of the region which is trapped. It's not fully true, so there's a lot of subtleties involved in that question. But the starting point for the analysis that I'm going to present is sort of this viewpoint, and not so much the global viewpoint of the event horizon that you learned. So now in what I'm going to talk about, there is one more definition you need to keep in mind. So that is, in fact, the most common thing that we will use. So it's called a marginally outer trapped surface, or MOTS. So this is the case when, in fact, I have theta L equal to 0 and no condition on theta n. So this refers to the fact that it's marginally trapped only in the outer directions, only along the L direction. And nothing is said about the N direction. Okay? So in this case, if we look at the causal nature, so the theta L vanishes. The theta N can be anything, can be future or past directed. So it includes this direction and also this direction. Okay. Good. So now comes the question, right? Let's try to visualize, or as far as we can, what does a trapped surface look like? What is its geometric nature? So first of all, it would seem very weird, right? So it is in Schwarzschild, these are exact round spheres that you're looking at. Okay? So in fact, the surface is in fact curved exactly in the same way. But nevertheless, the outgoing light rays are also converging as defined by the expansion. So now you might take it to mean that, well, and often I've also been guilty of doing the same thing, which is to say that, well, gravity is so strong that even the outgoing light rays are converging. But this is not the right way to think about this. Because, as you know, if the black hole is very large, gravity in fact can be very weak. Because the tidal forces go like m upon r cubed, so like 1 upon m square at the surface of the black hole. So the black hole is very, very massive. The tidal forces are very, very weak. So in fact, gravity doesn't have to be strong at all in those cases. So no matter how massive the black hole, how weak the gravity, it is still true that the outgoing light rays inside, just inside the horizon, are still converging. So this is like a genuine feature of a black hole spacetime. This is quite, it's not intuitive at all. And this, you just did the calculation yesterday, and this is what you found, right? So this is sort of the key, very, very non-trivial property that a black hole spacetime has. The existence of surfaces which are, well, marginally trapped and also completely trapped. Okay. Then there's a few other things that I will talk about here before moving on to the next topic, which is that in the expansions, I just look at the trace of these tensors. Right? So for the expansion, I said, well, I have this tensor grad ALB, I take its trace, then I get the expansion. But of course, there's more information hidden inside this tensor, right? So in general, for any such tensor, and by the way, these are two-dimensional tensors, so these are living on the sphere. So in this tensor, I'm always restricting these indices to be on the surface S. These are, in the case of a sphere, this would just be in theta and the phi directions on the sphere. Okay? So in general, I can decompose this tensor LB as a trace part, which would be half. So I'll write that in this following. Will be obvious in a minute why I'm doing this. So this is the trace of this. So I take out the trace, and that is a factor of 1/2 in there. Okay. That means that the rest of these tensors are traceless. This is the symmetric part, and that is the antisymmetric part. Okay. So this is the trace part. This is the symmetric. And this is the antisymmetric trace. So it's of course always trace-free because it's antisymmetric. Okay. So if you write this in terms of, let's say, a 2x2 matrix, so this will be of the form of A minus A, B, and B. On the sphere now, it's a two-dimensional case. And this would be of the form of 0, 0, C minus C. then this is known as a shear of L. And this is the twist. And in our case, in fact, for most cases, as we'll discuss again tomorrow, the twist of the null normals we use will be vanishing because, in fact, these null normals are, they form surfaces. So if we integrate them in time, then they will be tangent to a smooth surface. So the twist goes away. The shear is extremely important, though. And here you should make the connection to gravitational waves. Right? So all of you would have heard at some point that gravitational waves are given by psi4, the Weyl tensor component psi4, and conversely also in terms of the H plus and the H cross polarization. So that is also a symmetric trace-free tensor. So if you look at in the transverse traceless gauge, the form of a gravitational wave, what you find there is a form of this kind, H plus, H cross, and minus H plus. So imagine a wave going along the X direction, on the Z direction, then this would be the X and the Y direction, then you get precisely a symmetric trace-free tensor. So in fact, you can see the connection now of the shear of the L to a gravitational wave. And if you imagine now a little cross-section along this light rays, a little, think of at each time a cross-section, think of how it evolves, then the expansion means that if I start off with a cross-section like this, it just grows and remains a sphere. For the shearing motion, the area is preserved. So it then deforms in one direction and expands in the other direction. I'm not drawing this very well, but you get the point, right? And then, of course, as time goes on, it oscillate in the other way. And the twist is, again, it's not relevant for us generally. So this is just a rotation of the whole thing. So as we will see, the shear will be the infalling radiation at the horizon. The expansion, well, it vanishes at the horizon, but generally speaking, it shows you the growth of the light rays of this light bundle of light rays as it propagates. And the twist is usually not relevant in our case. So these are what are known as the optical scalars. So this is true not just it's true for light, it's also true for light in a medium, right? So I think a little bundle of light rays, it'll deform in a certain way. And you can always decompose that into these three different components: an expansion, a shear, and a twist. So these are the three sort of physical effects that are important here. And this is what is important, we will use to define what we mean by a black hole horizon. So any questions up to this point? So they are being parallel to each other. So if you go back to the Schwarzschild picture, and if you imagine light rays propagating along the horizon, so they're always remaining, they're not expanding, they're not converging. So it is geometrically a very, very weird thing, and it has very, very strong implications for what geometry of that surface is. And this, again, as we just saw, this will never happen in a normal sphere. Yes, for the trap surfaces, that would be somewhere here. Then a light rays would then converge to the singularities. There's one more thing which I should really emphasize. These are closed trap surfaces here. Okay. So of course, and the Penrose theorems apply to the closed trap surfaces. So now you can imagine that if I take, here, as of now, S is quite general, right? If I were to take S to be a plane, then of course the light rays would propagate parallel to itself, right? So think of then a plane completely flat, and the light rays would go in this way. Would have zero expansion in that case, right? Yes, it'll converge, yes. Yeah, it's hard to visualize. I mean, I've tried for many years. It's hard to visualize. In calculate, you can get the equations, you can know when the light rays would converge with where the focal point would be. So what you would see would be the light rays converging and getting a focal point. Well, we've not talked about the focusing theorem yet. I'm just sort of talking about what the expansion and the shear and so on mean, right? So we'll discuss that as well. But as of now, I've not talked about that. So I've not talked about the different sort of effects in how this expansion would evolve in time along this null geodesics. Yes. Yeah. That's a very good question. So it is in effect what you said about this focusing theorem. So this will be an equation as we will derive, or at least I'll write down the equation and tell you how to get it, or how the expansion and the shear evolve along the null generators. Okay. And in that equation, you will see the different terms that appear there. And you will see one term there which is coming from the Ricci tensor. So that you can interpret as the effect of the Einstein tensor and so on, even though that is zero in vacuum. But normally would satisfy energy conditions, so that's where you could think of gravity playing a role. Right, so where are we? Yes, so it is critically important here that we have closed trap surfaces. So if I have a sphere, if I have a plane, if it extends infinitely, so it's not a closed surface. And you can have such a space, such a plane inside the black hole, right? So that doesn't violate any theorem. If it's a closed surface, so and at some point the surface has to close back and become a proper sphere. If that happens and the theta L still remains negative or inside the black hole region, then you have a trapped surface. Also, it does not mean that every sphere here has to be trapped. You can have spheres of a highly deformed spheres for which it might even be expanding, theta might even be positive. But if there exists even one sphere for which is trapped, then you have a singularity in the future. Okay. So keep in mind that, in this, if I take each dot as a sphere, right? These are the spherically symmetric spheres. Of course, I can construct a sphere which is hard to depict in this Penrose diagram, which is non-symmetric. And those are very hard to understand analytically. Okay, so it's been a lot of work on that as well, but those are hard to visualize for students and even while doing analysis on those things. So you can construct spheres of that kind, which would not satisfy the trap condition. It doesn't matter. There are certain spheres which are trapped, and that is all you care. We know that the trap surface is a necessary condition for singularity. We also know whatever exact lattice there, either imaginary trap surface on the horizon or inside there's a trap. I know that there is a distributive result that start with initial data which does not have trap surfaces, but for a very special case, is it always guaranteed that gravitational collapse of any matter always leads to trap surface for any generic initial data? Well, all the cases, there's no theorem of that kind, but all the cases that we do know do satisfy that property. So it's one of those things I believe to be true. I can't prove it. So that is still a loophole in the yeah, so that could be. But the point is that there are, so let me try to see. So if you do have an event horizon, I think you could argue in the way that if I do have an event horizon, then I can deform the cross section of the event horizon inwards to make it trapped. Okay. That is always possible. So even if it's an expanding horizon, so expansion is positive. So I mean, you have to show, it requires some analysis. But late enough when the expansion becomes smaller, then I can also, imagine deforming it inwards and making it fully trapped. So I think that's why I can imagine proving such a result. So any other questions? This is again the conceptual starting point for the black. Yes. So these are all in one scenario, just the mathematical definition of what the surface is. And there will be certain times when I need some condition on this theta n. And in fact, in general, we will see that there are cases where theta n is not always negative. So on a sphere, the theta n will change from one point to the other. And there can be certain points where theta n is positive, in fact, even for a black hole horizon. So then the thing is that, well, then we say, okay, we proceed as before. Many of the results can still be shown, even for a MOTS. And so the MOTS condition is sort of the key thing in this whole business. But it so happens that generally speaking, theta n is also negative, like in Schwarzschild, it is the case. For highly distorted black holes, this may not be the case. But for the realistic black holes that we see from numerical simulation and so on, there are times at which theta n is not always negative. But eventually it always, in the end, it always becomes negative. So this is just sort of a mathematical thing for, it's the same physical scenario. It is simply that the theta n turns out to be a complicated condition as it turns out. Sometimes it holds, sometimes it doesn't, but in the mathematical framework still works. So any other questions? No, so I mean just that. So we're looking at the moment, I've not talked about time evolution at all of any of these things. So there's nothing. So I'm just thinking of different spheres in a given space-time, and I just calculate the expansion for those spheres. So like in Schwarzschild, I could take a sphere inside here, out here, on the horizon here, and here. Sorry, could you repeat that? Well, I mean, the mathematical theorem itself, the Penrose one, requires both to be negative. So we never found a condition in sort of black hole collapse or black hole merger where theta n is everywhere positive. So it is generally speaking positive in a little bit of area, a little bit of portion of the surface, but otherwise it is negative. So I don't know of any sort of normal case where theta L is 0 exactly and theta n is everywhere positive. That would be strange. By the way, just, we won't deal with it here. So if you look at sort of the white hole region, then in fact, it's fully untrapped. So in that case, both theta L and theta n are positive. There is all the time reverse versions of this thing. Okay. So in that case, this mean curvature vector lies here. That is the white hole region. And again, you can work out the causal nature of the mean curvature vector in the different cases. So I will still not define dynamical horizons for you yet. So next, I would like you guys to calculate practically how to locate margin trap surfaces. Okay. And for this, we will look at initial data sets. So this again goes back to the, this formalism of submanifolds, but now we will look at the case of codimension 1, the standard initial value problem in GR. So you'll forgive me for the same notation. Well, let's not call it n here. Let's call it big N, okay? That is the unit time like normal to the surface. In this case, the 3 metric on this, let's call it H. And let's call the unit time like normal to be big N. And let us call then, again, as before, the derivative operator on sigma to be D, and on this big space M with G and So now you know how this whole formalism works. So you start off with some time function. So you see that in my whole manifold, I have some time function, and surface of a fixed time are these surfaces here. Then given the time function, I can construct the vector, the time evolution vector, which is partial derivative along t. I will point out that this seems like a simple thing to write, but this implies some spatial coordinates as well. Because what does d by dt mean? It means I move along time, keeping all the other coordinates fixed. So I cannot even talk of this vector unless I introduce the other coordinates. What is being kept fixed, right? So I'm keeping fixed the spatial coordinates. I'm moving along time-like direction at a fixed spatial position. So this, in effect, involves then the lapse and the shift functions. I won't discuss that in detail here, but that involves then the projection of this d by dt along the n direction or along the spatial direction. And the spatial direction tells you how these coordinates are sort of adapting to this time evolution vector. That is a shift vector there. Okay. What is important for us are the constraint equations that are satisfied from this by this data on sigma. So again, I will not prove this here, and I hope that you've seen it all somewhere before. So just like it happens in electromagnetism, so if I look at the Maxwell equations, so you have the time evolution vectors for the electric and magnetic fields, but then you have the Gauss law equations for the electric and magnetic fields. So those do not involve any time derivative. Those are just equations to be satisfied at any given time. In a similar way, we have equations from the Einstein equations, certain parts of those equations which do not have any time derivatives. So those are called the constraint equations. Those have to be satisfied at each time. Okay? So let me just write those constraint equations down. And I will always get the sign wrong here. So this is 3r plus k squared minus k. This will be a matter term here involving the mass density. And the other one is then the momentum constraint. I mean, the signs may be wrong. Doesn't matter, we'll set them to 0 anyway for what we do today. So this k is the extrinsic curvature, again coming from the second fundamental form. This 3r is a Ricci scalar from the metric h. So it's a is the Ricci scalar intrinsic to this spatial surface. It is not the 4-dimensional Ricci scalar there. So just given the 3 metric with the usual equations for the Ricci tensor, you can calculate what this 3r is or as a function of spatial coordinates. Okay. So have you all seen this before at some point? I mean, is this just completely Greek to you, or have you all seen this at some point? Yeah, this is the Gauss-Kodacki equation. So you've not, so it's not, okay. Well, unfortunately, if I derive this, this will just take me too long. So all I can say is that, well, if you look at the full Einstein equations, decompose them into, look at the different parts involving the time derivatives and not the time derivatives, then you can show these two equations must hold at any given time. And again, you note that this does not involve any time derivatives here. So the data to be prescribed is the metric and the extrinsic curvature. And with that, they must satisfy these conditions. And then you can do evolution in time. Then at a later time, you get the metric and extrinsic curvature as a function of. So that is a general framework. But for today, what we need is just to understand that, well, if I have a given surface, then if this is in a space-time and the space-time set of Einstein equations, then the metric and the extrinsic curvature must satisfy these two constraints. Then we will simplify this further just to look at a very nice simple example. So we will look at the case when the extrinsic curvature is 0 precisely. Okay. This is known as a time symmetric initial data. So that means if you evolve further in time or backwards in time, you get the same result. Imagine throwing a ball up, right? at the moment at the highest point, this is the moment of time symmetry. So the motion is same backwards in time or forwards in time, starting from that. This is like two black holes going apart, stopping and then coming in, right? So this would be then the initial data at the time when the black holes are at rest. So we will then look at the case when this extrinsic curvature vanishes and is vacuum. So we will set all the matter density and the matter currents to 0. Then the only equation that we have is then the scalar curvature has to vanish. We'll make now one more condition, namely that the metric is conformally flat. That means that this H is some conformal factor to the 4th power. Will just a conventional, you'll be clear why the 4th power times the flat metric. So in the end, all of this being satisfied, this is the collision of two non-spinning black holes in a head-on, as a head-on collision of these two black holes. Okay. And it can be shown, again, I will not do it here, you're welcome to work it out yourself, which is that if you impose conformal flatness, and if you look at this equation of the 3 Ricci scalar being 0, this is the same as the Laplacian of the conformal factor being 0. And this is the Laplacian in this flat background. So it's exactly like electrostatics. A point charge, it has the potential satisfy Laplace equation. This is precisely that situation here. Or for a point mass in Newtonian gravity, the gravitational potential satisfies then the Laplace equation and get the 1 upon r. It's exactly that equation. So the beautiful thing is that all the complications of GR that are involved here, it all simplifies to this very simple Laplace equation. I'm not proving this for you, so I mean, it's not that difficult, but would just take me a long time to sort of do it, and we don't have that much time here. So now let me sort of tell you a case from Schwarzschild where this appears naturally. So to make the point that there's nothing exotic, and this you can in fact already see in the Schwarzschild case. So look at the Schwarzschild metric space-time here. And look at this particular slice of Schwarzschild, a straight line going from here to here. Okay. So this is so if I take first of all any slice in Schwarzschild, the constraint equation holds on all of them. Okay. If I take this particular slice of Schwarzschild, then you can show that in fact the metric on this slice, and it's best using a different coordinate system known as isotropic coordinates, that the metric on this slice is of the form here, which is H. B is 1 plus m upon 2r to the power 4, and then dr square plus r square. So I claim that this is the metric, the 3 metric on this slice here. This is the point r equal to 0. In fact, in this is not the standard Schwarzschild coordinate r. This is what is called the isotropic coordinate. Okay. Because in the normal coordinate, this would not be of this conformally flat form. You got to make a coordinate transformation, and this involves isotropic coordinate. In those coordinates, then it is in fact conformally flat. The nice thing is that the rest of the metric is completely the Euclidean flat metric. And also you notice that this is r equal to 0. While here, if I put r equal to 0, it seems to diverge. And then you can show, which is in fact one of the exercises, that to make a coordinate transformation, and show in fact that this in fact is not a real divergence. It is in fact just the other asymptotic end of this slice. Now, the other thing to keep in mind is the topology of this slice. So this, I guess, you have seen before. This is the wormhole topology, right? Because we start off, what is happening here? Here I have large R. I'm thinking of now the Schwarzschild R, okay? So now this isotropic R. Think of now the Schwarzschild radial coordinate. So there, these are large spheres. The spheres become smaller and smaller. At this point, R is 2m. So the spheres are the smallest at that point. If I continue here, the spheres again become large. Right? So the topology looks like this. And the throat and the sort of the smallest radius is exactly the horizon, and that is this point here. So this, I presume you all have seen, right? I hope this is not a mysterious thing. So in the Kruskal diagram, this is what the topology of this slice is. So have you all, can you just have raise a show of hands who has seen this wormhole kind of thing before? Okay, so that is good. So I'm happy to see that. So this everybody knows. What you may not have known is that the metric on this slice is given to be of this form. And here you see that the conformal factor is exactly 1 upon R. So it satisfies the Laplace equation and is to the power 4th. Okay? And that is the reason, in fact, why it's convenient, it turns out to be good, to take phi to the 4, then that phi will satisfy the Laplace equation. So any questions about that? No, as I said, so this is isotropic. This is not the standard Schwarzschild coordinate. And also keep in mind that this is, you might be surprised here, this is m upon 2r, not 2m upon r like we expect in Schwarzschild. So this is not the usual Schwarzschild r. There's a different radial coordinate called the isotropic coordinates, which is in fact is 0 here and is infinite here. So it just grows in this direction. It takes some work to show that you can recover this from the usual Schwarzschild r. So that's exercise for you if you would like to try it. What you have to do is to find an r such that the 3 metric is conformally flat. Maybe that's an exercise for the tutorial. It's not there at the moment, but if you wish to do it, then you're welcome to try. Yes. So then that's a different, you're talking about how to construct black hole initial data for rotating black holes. So that is a big topic by itself. That is sort of finding solutions to these equations with the right conditions. So what is required in that case is to find a solution first for the momentum constraint when this k is not 0. It turns out, it was done by York, that you can in fact solve this equation, get a solution for it with some nice conditions of angular momentum and linear momentum. So that gives you k. You plug that into here and you solve then for the 3 metric from the other equation. So I won't discuss that. This is not the purpose of this lecture, but that is generally how you do it. And that is the starting point, in fact, for most numerical simulation that you will see for binary black hole mergers. No, they're not the same as Kerr. So there, in fact, you take conformally flat in most cases, so it's not Kerr. But what happens is that after a short time, it becomes close enough to Kerr that it doesn't matter. So Prayush will know all about this, or no? You have a local expert here so to ask. Any other questions? Okay, so what we will do now is this, I think it's one of the most delightful calculations in GR, which is to notice that just solving this Laplace equation gives you solutions to the Einstein field equations in this case. Okay. So let me try to represent now the Schwarzschild case as a solution for the Laplace equation. So from this point, forget about GR, just think of electrostatics if you wish, or it's a point mass in GR. Okay. So think of the spatial slice. This is, let's write it like this. Then you have what is called a puncture, that is the point r equal to 0. That for the Schwarzschild case would be the other asymptotic end, would be this point here. Okay. Then the solution to the Laplace equation, you know, has to be 1 upon r. Call that alpha 1 upon r. There is one difference here though, which is that the boundary condition is we want that at large distances, phi should go to 1 and not to 0, right? Because if the metric were to be 0, that's sort of a strange case. And this is what you normally do for, let's say, in the gravitational potential or for electrostatics. But here that is the one difference. So we say it should be 1 plus alpha 1 upon r. The 1 just ensures that at large distances, I get the standard asymptotically flat condition. Okay. So this, in fact, just solution of this equation and what you know from electrostatics. This is the general solution for Laplace equation for a point source, right? And this alpha 1 turns out to be m over 2. And this is then the solution, the simplest solution with one puncture for the Laplace equation. And this gives you then the 3 metric, and therefore then the entire geometry of that spatial slice. But we can go further now, right? Because this is a linear equation. That is the other beautiful thing about it. So I can take multiple point sources. So I could in fact take n sources. I could take these to be at positions, let's call it Ri. And the solution is obvious. So in this case, solution is 1 plus sigma I alpha I upon Ri. Where Ri, so, okay, let me call it Ri. By this I mean simply the distance to the ith puncture, okay? Or if you wish to be very explicit, this is R minus R. Okay, so this is then the solution for n point sort of sources. It satisfies the Laplace equation except at those punctures. And this is then also a solution to the Einstein constraint equations. So this represents in multiple black holes, and this represents the solution for the conformal factor, and therefore a solution for the constraint equations. So in this formalism, it is then beautifully simple to include n black holes, and then you get the 3 metric on this spatial slice for n black holes. But what is the topology of this slice now? So there we had just one wormhole condition, right? So here then we have multiple wormholes. So imagine the case now for 2 black holes, and that is what we'll actually do today. So in that case, for 2 black holes, the conformal factor is 1 plus alpha 1 upon R minus R1 plus alpha 2 upon minus. And the other nice thing is that now you can simply forget about curve space. These are now just vectors in Euclidean space. This is the conformal space now. These are just vectors in flat space. And everything that you know about the Newtonian gravitostatics or electrostatics, everything applies here directly. Of course, the alpha should be positive, so negative would be a problem, negative mass. Well, I mean, it doesn't Well, we're not adding it that way. I'm just saying that this is the solution. So this satisfies the Laplace equation, and the boundary condition that at large R, it is 1. Right? So this is then the solution to that. Okay, what is the topology of this slice? Well, in the simple way of looking at it, this is just a R3, just flat Euclidean space with 2 punctures, right? And at any point, this is the distance then R1, and this is the distance then R2. Yes. Well, there's no justification. So this is simply a way to get initial data. So we justified it initially by saying, well, in the Schwarzschild case, it is conformally flat. Well, of course, there are other slices of Schwarzschild where it is not conformally flat, right? So the game here is not to justify that. It's just to say, well, this is a way to get initial data, having 2 black holes, and there's a way to then evolve this in time. And what normally happens is that even if the initial condition is not, astrophysically the right thing, once you evolve in time, it settles down to the right solution that you really want. Okay, so then at least in the Euclidean level, it's clear what the setup is, right? But now from a GR point of view, what is then the topology of such a slice? Well, it's the following. It's 2 wormholes, in fact. So once you go close to each of the black holes, each of these punctures, these are in fact not singularities, even though it might seem like if R goes to Ri, this becomes infinite. But in fact, it's not. You can make a coordinate transformation just like you did for the isotropic case and show that in fact the metric is asymptotically flat at these punctures. Okay. So therefore, there are 3 asymptotic ends in this problem. There is an asymptotic end here for 1 puncture, then for the other puncture, and 1 end for the whole sort of spatial slice. Okay. Is the setup clear? This again might be something completely alien to most of you, but this is the standard, this is sort of the easiest of the initial data problems that we have in GR. It's easy enough that you can actually do detailed calculation, which is what you will do today. But is the setup clear? So this is usually not how you're taught this subject of a 4-dimensional, beautiful 4-dimensional space-time. This is now when you want to find the right solution to Einstein equations, you have to evolve things in time. And that means that you have to choose some time slice, and that brings in all of these complications. So all the beautiful 4-dimensional solution that you all know, none of that is useful. So that's one more reason why event horizons are not useful, because once you evolve this in time, you have no idea where the event horizon is. You can trace it back, you have to wait for the full simulation and locate where the event horizon is. But while you're evolving, or even in this, you can ask the question, which is what we will solve, in this binary black hole space-time, where is the event horizon? We don't know. But we can in fact find where the marginally trapped surfaces are. So then the use of these marginally trapped surfaces, of course, there's this theoretical thing which people might like. There's a purely practical matter. Once you are in this frame of mind that you have to evolve things in time, you need to know where the black holes are. So then you say that, well, locating a MOTS is how we practically say that there is a black hole in our space-time. Right, and for this purpose, event horizons are of no use whatsoever. Okay. So what we will do now is to in fact locate a MOTS on this binary black hole space-time. Okay. So half an hour. So Doing better, not as well as I like, but still can be done. Okay, good. So now let us understand the problem of finding a mods on a spatial slice. Okay, and we'll apply that now to both of these cases. So this is then a spatial slice. Imagine you have a sphere here. And I want the condition such that this sphere is a MODS. So the first thing is that I can construct the null normals in an obvious way. I have the unit time-lag normal that is big T. And on the spatial slice, I have the unit normal, let's call it big R, unit vector, the radial direction that is of unit length in the proper metric now. So this I'm presenting in a general case. It doesn't have to be conformally flat, but this part of this is fully general. Then the outgoing null normal is just T plus R, and the ingoing one is just T minus R. Right? So this is L, and this is N. So we can take L to be okay. So again, given the sphere, I have the radial direction, I have the time-lag direction, I can construct just from those what the L and the N are, right? Then the other important thing, how do I get the two metric on the sphere? So I'm given the three metric on the slice, HAB. So the two metric here has to be, call it Q tilde AB, has to be HAB minus so it's minus because it's a space, this whole thing is not space-like. So then with this two metric, I want the condition that this L has to have zero expansion. So that is a MODS condition. In a minute, we will write the equation and solve it in a, for this. This is, by the way, known as a Brill-Lindquist initial data. So this based on the two people who did it. So this framework of time symmetry and conformal flatness, that is called the Brill-Lindquist initial data. In fact, if you look at the Brill-Lindquist paper, you'll notice that they do the case for including electric charge as well. So black holes can be charged for them. And they find the condition says that two black holes can be static, that the charge electric force cancels the gravitational force. So it's a very interesting paper. So I encourage you strongly to read that paper. Okay, good. And one more thing which I forgot to mention, which is the notion of an apparent horizon. So an apparent horizon is the outermost MODS or outermost margin trap surface on any spatial slice. And you will ask why outermost? As we will see, there's a huge, even in this simple binary black hole case, there's a huge variety of surfaces that we will find, all of which are marginally trapped. Okay? And the outermost one of those is the apparent horizon. All right, so now let us, I should really hurry up because I need to show you the numerical results as well. So let us now write the equation for the conformally flat, for the zero expansion condition. So what I want to know is that I want Q tilde AB. This is the condition for the MODS, right? I want a two surface S such that this condition is true. So let us write down what this condition would be. So this is Q tilde AB. So for L, I choose this condition here. And the root 2 doesn't really matter. I mean, it's just an annoying factor for the normalization condition. I just take T plus R here. Okay. So TB plus. So this has to be then 0. Okay, all with me so far? So this, I put in now the Q tilde coming from here. So then I get HAB minus R hat A, R hat B, then, sorry, dA should be. This is the three-dimensional derivative. Then I have T plus R. So let us now collect the terms. So then I have again HAB minus RA. So here first notice I have dA and TB. That is just the extrinsic curvature. So that is just then KAB. Then I have the DARB. Let's keep that as it is. Zero. Then when this H hits the K, that is just a trace of the extrinsic curvature. That is simply K. Then when R hat A, R hat B hits this is just one component of K. Now in this term, when the R hat B hits this, that is just 0 because I have R hat B times D of R hat B. R is unit norm, so then this is 0. And I only have then this multiplying this, and that is the three divergence of this R. Right? So that is simply then D, A, R hat A, 0. So this is the equation to solve on the spatial slice to locate the mods. Locating a mods means, in fact, to find, in effect, this vector R hat, which is a normal to this. That's a gradient of some level set function defining the surface. And that is what you look for analytically or numerically in most cases. In our case, now we go back to the Brill-Lindquist calculation. We have 0 extrinsic curvature. So both of these terms are 0. We then only have to solve the equation, which is a divergence-free condition, is 0. Okay. So this is all I need to do for the Brill-Lindquist case. So any questions up to this point? Because for Brill-Lindquist, the extrinsic curvature is 0. So both of these terms are then 0. Any other questions? Okay, good. So now let me demonstrate to you that for the how to then find the solution for the mods in a Brill-Lindquist data. Okay. So now let us go back to this construction here. Then the distance between the punctures. Now this is distance just in the Euclidean sense. Now just think of normal flat space. I take two punctures at some distance d apart. So that is this d. And by the way, the proper distance between the two punctures is infinite. Okay, so that's a complicated thing. But at least in this flat Euclidean space, it's a finite sum, just known distance d between those 2 points. Right? Then I just need to then find the equation here to solve this equation, and we get the solutions. It seems really simple, but as we will see now, it's an extremely complicated problem. We will, in fact, it is simple in one sense. It is that for a single black hole, it's obvious how to do it. For two black holes, for large separations, you will do it in the tutorial. But when the distance becomes small, the black holes are close to each other, then all the complications arise. Okay. And the other thing to keep in mind, which we will not discuss, this condition here is the same as what you get for a minimal surface. So these are surfaces, if you want to ask the question on a variational principle, even in this room, I construct, I want to get a two surface, which has minimal area, which the area function is a minimal under perturbations. That leads to the same equation. It is also same as the mean curvature 0, yes, that is right. Because, yeah, all the expansions are 0 in this case. That is to do with time symmetry because, theta, L, theta, and they're time symmetric versions of each other. So this is time symmetry. That's why then all the expansions vanish at this time, this initial time. Once you evolve the data, then at later times, the metric is not conformally flat, and the moment and the extrinsic curvature is not 0 at later times. It's only in the initial data this is true. No, here the minimal surface, I just simply mean minimal of the area functional, that's all. In the classical, Euclidean sense. It's not the minimal surface as you would properly do it here. It is in this flat background always as a minimal surface. Well, no, it's not true. No, sorry, I take it back. So on this slice with 0 extrinsic curvature, it is actually the minimal surface. It is 0, right? So Brill-Lindquist, it is 0, yeah. Yes. Okay, so let me now set up the problem. I hope I have enough time to show you then the results as well. And it's important I do this because this is what you will do in the tutorial. So let us now think of the case when D is large. And I look at one of the punctures, right? So I'll imagine I want to find a surface around one puncture. The other puncture is far away. Okay? The distance D is much larger than the size of this mods that we will find. Okay? So now set up usual Cartesian coordinates or spherical coordinates around this point. And in the present case, what we will also do is to keep the other black hole on the z-axis, far away. Okay, so it's not here, or the z-axis goes along here. So in the present case, the other puncture is somewhere far away up there. Okay? So that means that this surface will be symmetric in this direction. Okay, because this is the axis of symmetry of the whole situation. So then whatever surface I find here will be axially symmetric. So I just need to, in fact, find this circle in this plane of theta. Okay? So let us now say that this is then the point on the surface. This is the angle theta. And I look for a level set of a function which is f is r minus h of theta. And this h is what I want to find. H is the height function that we have here. Imagine the surface can be highly deformed. Then for each theta, I get a height function. So the level set I want to find is of the function r minus h theta. So when f would be 0, then r would be h of theta, but that comes later. I want to find level sets now of this combination here. So therefore, for a level set of such a function, I want to find then this vector r hat and plug it in here and set up the equation for doing this, finding this minimal surface. So let me do that now, and we're very careful here to take in factors of the conformal factor. So to keep track of that, apart from that, everything is in the flat space. Okay, so that is the one tricky thing to keep track of. Okay, so let's do then the differential. So df is dr minus h theta d theta. Okay. Now, what is the metric? Well, the metric is conformally flat in these coordinates. So the metric is simply Q is simply is phi to the 4th. Then I have dr square plus r square d omega square. Okay. So in matrix form, then the metric itself is phi to the 4th, 1 r square sine square theta. So that is, sorry, this is h. And the inverse metric is just phi to the minus 4th, 1 upon r square, 1 upon r square. Okay. And one more thing, Willie, is a determinant of the metric h. That is also easy to get. Determinant of h will be, it's a three-dimensional case, so it's phi to the 4th cubed. So it's phi to the 12th, then r to the 4 sine square theta. So the square root of the determinant of h will be phi to the 6th r square sine theta. Okay. So now we can calculate what the unit vector r is. Let's do that here. So the unit vector r, I first look at df, I raise the index and divide by the norm of df. So let us first do that. Let us first raise this index here. So df was this guy here. I raise this index first, and each time I get the conformal factor take into account. Okay. So if you do that, I claim the solution is the following. Will be phi to the minus 4 del by del r minus h theta on r square. I mean, you can see how this is, right? So you get first this one, inverse of that, this one, well, right, we need this guy here, so it's 1, so that's just 1 here. This is 1 upon r square. So in the second term, this h theta upon r square, that is this term here. And there's nothing for the phi, we don't care about that. And there's an overall conformal factor coming from this. Is that clear? Any questions on that? Because this, you will do a more complicated version of this in the tutorial, okay? You better understand this properly here. Then the norm of df square, let's do square first, the norm of this guy here. Just a diagonal metric, so I just need to look at the norm of this and the norm of this. So that turns out to be, and you can check the numbers here, phi to the minus 4 times r square plus h theta square divided by r square. So it's important to keep track of this confound factor here. It's always, in this case, is 5 to the minus 4. Okay. But the norm of df is the square root of that. So that is 5 to the minus 2 divided by r times r square plus h theta square and the square root. Okay. So therefore, finally, the unit vector r is then the ratio of this to this, or this to this, in fact, and that turns out to be the following. So that is 5 to the minus 4 upon 5 to the minus 2 r, and then I have here r square plus h theta square. Then I have here minus okay, so this becomes, after cancelling out the confound factor terms here, will be r upon phi square, and I have r square plus h theta square, and I have del by del theta minus h upon square, sorry, del by del r. Okay. So now finally we are done. Then I'll have a divergence of, I want a divergence of this vector. So dA of r hat A is 1 upon the determinant of H. Then I have del by del x mu, then determinant of H times this r hat. Right? And here you have first derivative of r and then of theta. The phi doesn't matter. So if you now use this vector here with this component and this multiplied by this component for the theta direction, and you plug it all in here, then you can show, and this is then the starting point for a tutorial today, this equation becomes the following, which is del by del r of phi to the 4th r cube sine theta upon r square plus h theta square equals del by del theta of 4th r h theta sine theta divided by r square plus h. Looks complicated, it is complicated, but it can be solved for large separation. So any questions about this? No, all clear? Then at leading order, so then I have a solution of this equation. I have to find the h. So I can expand the solution in powers of 1 upon the distance. And then you'll get an expansion of some first order term, then the first effect of the other black hole, then an inverse powers of d, higher order effects from the other black hole acting on this first black hole. Let us very quickly apply this for the single black hole case. Okay? That will be quite easy. Because in that case, so this is then the equation in general. Then for a single black hole case, it's spherically symmetric. So all the theta derivatives go away. This sine theta also doesn't matter here. This h theta also doesn't matter. So therefore, the equation in spherical symmetry is simply, and that is a leading order solution also to the binary black hole case, in fact. So that just becomes del by del r of phi to the fourth times r cubed divided by, now this goes away, so this is just an r square square root, so just an r. So it's just phi to the fourth times r squared. Right? You notice this is just a square of phi squared times r. So this is then simply del by del r of r times phi square is 0. Now phi for the spherically symmetric case is just 1 plus alpha 1 upon r. So this is then simply, can you still see here? Well, it's del by del r of r times 1 plus alpha 1 upon r whole square is 0. Just expand the square, multiply by r, take the derivative, then you will find that r in fact is alpha 1. And alpha 1 is m by 2. So in isotropic coordinates, the horizon, this apparent horizon, is at not 2m, but at m by 2. And with the coordinate transformation to the isotropic coordinates, then that goes back to 2m. But if you find the area of this horizon, it is the same as in the short shell case. So at this point, I had meant to show you numerical results for the small separations. So we're out of time, so I will do that then tomorrow. Okay. So I still haven't talked about dynamical horizons, but important that you need to understand how to locate these modes here. So any questions before we stop? Because r phi square is, I mean, this is the square of that, right? If del by del x of, let's say, f square is 0, then del by del x of f is also 0. Okay, so we'll stop here and then we continue tomorrow.